The ocean can look calm enough to mirror the sky. A flat horizon, a slow rhythm of waves, nothing that suggests danger. Then, without warning, the sea begins to behave in a way that feels wrong. The water pulls back from the shore, exposing rocks and sand that are usually hidden. Boats tilt awkwardly. People step forward, curious. Minutes later, a wall of water arrives, not like a crashing surf wave, but like a rising flood with unstoppable force. This is a tsunami. It does not form where you see it. It begins far away, often deep beneath the ocean, where forces far larger than weather are constantly reshaping the planet. To understand a tsunami, you have to forget everything you think you know about waves. These are not created by wind. They are not surface ripples. A tsunami is energy moving through an entire column of water, one from the seafloor all the way to the surface. It can travel across entire oceans at the speed of a commercial jet, yet remain nearly invisible in deep water. By the time it reaches land, that hidden energy transforms into one of the most powerful natural forces on Earth. What creates that energy begins with the structure of the planet itself. The outer shell of Earth is divided into massive slabs called tectonic plates. These plates are constantly moving, usually at speeds of just a few centimeters per year. Along certain boundaries, one plate is forced beneath another in a process known as subduction. These zones are where the largest earthquakes on Earth occur, and they are the primary birthplace of tsunamis. Beneath the Pacific Ocean, along what is often called the Ring of Fire, these subduction zones form a nearly continuous chain. Plates such as the Pacific Plate, the Nazca Plate, and the Indo-Australian Plate are all interacting with surrounding continental plates. Over time, stress builds as these plates lock together. When that stress is finally released, the seafloor can shift suddenly by several meters. In some cases, sections of the ocean floor, hundreds of kilometers long, are lifted or dropped in a matter of seconds. That sudden vertical movement is the key. Water is nearly incompressible, so when the seafloor moves, it pushes the entire column of water above it. Imagine lifting one end of a massive pool. The water has no choice but to move. This displacement creates a series of waves that radiate outward in all directions. Unlike wind-driven waves, which only affect the surface, a tsunami involves the full depth of the ocean, which can be several kilometers. Like in deep ocean water, a tsunami behaves very differently than it does near the coast. The wavelength, which is the distance between wave crests, can exceed 100 kilometers. The wave height in the open ocean is often less than 1 meter, making it almost undetectable to ships. But the speed is extraordinary. A tsunami can travel at 700 to 800 kilometers per hour in deep water, comparable to the cruising speed of a jet aircraft. You could be standing on a ship directly above a passing tsunami and not notice anything unusual. There is no dramatic crest, no crashing foam. The energy is spread out over such a long distance that the surface appears relatively calm. This is why tsunamis are so dangerous. The real transformation happens only when the wave approaches shallow coastal waters. As the ocean depth decreases, the physics of the wave changes. The bottom of the wave begins to interact with the seafloor, slowing it down. However, the energy carried by the wave does not disappear. Instead, it is compressed into a shorter wavelength. As a result, the wave height increases dramatically. This process is called wave shoaling. By the time the tsunami reaches the coastline, it can rise to heights of 10 meters, 20 meters, or even more in extreme cases. The wave does not always appear as a single towering wall. Often, it arrives as a fast-rising surge of water that floods inland with incredible force. Multiple waves can follow, spaced minutes apart, each one potentially larger than the last. One of the most well-documented examples occurred during the 2011 Tohoku earthquake in Japan. The earthquake itself measured magnitude 9.0, one of the largest ever recorded. The seafloor shifted dramatically along a subduction zone east of Honshu. In some locations, the tsunami reached heights of over 40 meters. Entire towns were inundated within minutes. The wave traveled across the Pacific Ocean and was detected along the coasts of North and South America hours later. Another major event took place in 2004 in the Indian Ocean. A magnitude 9.1 earthquake off the coast of Sumatra generated a tsunami that affected multiple countries, including Indonesia, Sri Lanka, India, and Thailand. The waves traveled thousands of kilometers, with some areas experiencing run-up heights exceeding 30 meters. More than 230,000 people lost their lives, making it one of the deadliest natural disasters in recorded history. Earthquakes are not the only trigger. Underwater landslides can also generate tsunamis. When large volumes of sediment suddenly collapse and move downslope, they displace water in a similar way to an earthquake. These events are usually more localized, but they can still be extremely destructive. In 1958, a landslide in Lituya Bay, Alaska, triggered a wave that reached an astonishing height of 524 meters. This remains the highest tsunami run-up ever recorded, though it was confined to a narrow bay. Volcanic eruptions can also produce tsunamis, especially when part of a volcano collapses into the sea. The 1883 eruption of Krakatoa in Indonesia caused massive explosions and caldera collapse, generating waves that reached over 30 meters in height and devastated nearby coastlines. More recently, the 2022 eruption of Hunga Tonga Hunga Ha'apai produced a tsunami that was detected across the Pacific, even reaching distant shores like Japan and the west coast of the United States. Coastlines themselves play a crucial role in determining how a tsunami behaves when it arrives. A wide, gently sloping continental shelf can cause the wave to build gradually, increasing its height over a larger area. Narrow bays and inlets can amplify the wave through a process known as resonance, funneling the energy into a smaller space. This is why certain locations experience much higher impacts than others, even when they are at similar distances from the source. The shape of the coastline, the underwater topography, and even the presence of natural barriers like reefs can all influence the final outcome. In some cases, a tsunami can wrap around islands or reflect off underwater features, creating complex patterns of wave interaction. This makes predicting exact impacts extremely challenging. Detection systems have improved significantly over the past few decades. Networks of seismic sensors can quickly identify large underwater earthquakes. In addition, deep ocean assessment and reporting of tsunami systems, known as dart buoys, measure changes in water pressure on the seafloor. These sensors can detect the passage of a tsunami wave and transmit data in real time to monitoring centers. Once a potential tsunami is detected, warning centers analyze the data and issue alerts to coastal regions. In the Pacific Tsunami Warning Center plays a major role in coordinating these efforts. Warnings can be issued within minutes of an earthquake, providing critical time for evacuation. However, the effectiveness of these systems depends heavily on public awareness and response. In some cases, natural warning signs appear before official alerts. A rapid withdrawal of water from the shoreline is one of the most recognizable indicators. The ocean may recede hundreds of meters, exposing the seabed. This is not a safe opportunity to explore. It is a sign that a large wave is imminent. The time between this retreat and the arrival of the tsunami can be just a few minutes. Tsunamis are often misunderstood as single events, but they typically occur as a series of waves. The first wave is not always the largest. Intervals between waves can range from 5 minutes to over an hour. This means that returning to the coast too soon can be extremely dangerous. The energy in the system can persist for hours. The impact of a tsunami is not limited to the initial flooding. The force of the water can carry debris, including vehicles, buildings, and trees, turning them into projectiles. As the water recedes, it can drag objects and people back toward the ocean. Infrastructure damage, contamination of freshwater supplies, and long-term environmental changes are common after major events. Despite their destructive potential, tsunamis are relatively rare compared to other natural hazards. Most large tsunamis occur in the Pacific Ocean due to the high concentration of subduction zones. However, they can happen in any ocean basin. The Atlantic Ocean has fewer active subduction zones, but events such as the 1755 Lisbon earthquake generated a tsunami that affected Portugal, Spain, and even parts of North Africa. The Mediterranean Sea, though smaller, has also experienced tsunamis due to its complex tectonic setting. Historical records describe waves impacting coastal cities in regions like Greece and Italy. Even inland seas and large lakes can produce tsunami-like waves under certain conditions, though these are usually much smaller. Understanding tsunamis requires thinking in terms of energy transfer. The initial trigger, whether it is an earthquake, landslide, or volcanic eruption, transfers energy into the ocean. That energy then moves outward, interacting with the depth and shape of the seafloor. As it approaches land, it is compressed and amplified, transforming into a powerful surge. The key difference between a normal ocean wave and a tsunami lies in how that energy is distributed. Wind waves are driven by the transfer of energy from air to water at the surface. They have short wavelengths, typically tens to hundreds of meters, and their energy diminishes quickly with depth. Tsunamis, on the other hand, involve the entire water column. Their wavelengths are enormous, and their energy can travel vast distances with minimal loss. If you compare the two side by side, the contrast becomes clear. A typical ocean wave might travel at 30 to 50 kilometers per hour and break near the shore with a height of a few meters. While a tsunami can move 10 times faster and carry vastly more energy, even if it appears small in the open ocean. The scale is fundamentally different. There is no way to stop a tsunami once it has formed. The focus is on detection, warning, and preparation. Coastal communities in high-risk areas often have evacuation routes and designated safe zones. Education plays a critical role. Knowing the signs and understanding the timing can make the difference between life and death. When you look out at the ocean, it is easy to see only the surface. But beneath that surface, the entire system is connected to the dynamics of the planet. The movement of tectonic plates, the shape of the seafloor, and the depth of the water all combine to create conditions that can produce a tsunami. It is not just a wave. It is a transfer of energy across an entire ocean basin. The next time you see the sea stretching out to the horizon, consider what lies beneath. Forces are constantly building, shifting, and releasing energy on a scale that is difficult to imagine. Most of the time, that energy remains hidden. Occasionally, it rises to the surface in a way that reshapes coastlines and changes lives in a matter of minutes. Be curious and always seek to learn something new. Subscribe and see for yourself. Thanks for watching.